Welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're joined by Steve Vogt from Lick Observatory in Santa Cruz University. Steve did his graduate work at Berkeley in the Bay Area and spent some time out of California for his graduate work at University of Texas at Austin, where he worked on the precursors to CCD arrays. So I hope that doesn't date him too definitively. But he's been doing work since his work at UT. He went straight to Santa Cruz, where he's been working ever since. And now he's going to tell us about his work on the exoplanet survey that he's been working on with Jeff Marcy and a host of other UC Santa Cruz people here. So if you'll join me in thanking Steve for coming along this morning.
Thank you very much, Adrian. This is my first visit to SETI, so I was kind of surprised to see how large the organization is here. But it's very nice to come over here and visit. I should have done that a long time ago. So what I'm going to be talking about today, as Adrian pointed out, was our work on the search for extrasolar planets around nearby stars. And this is work that was originally started by my first graduate student, Jeff Marcy, back in the 80s, and then carried on with, well, he and Paul Butler, basically, who was his postdoc. In recent years, the teams have split, and we have several teams now. The team that I'm now involved in is called the Lick-Carnegie Planet Search Team, which is myself, Paul Butler, Greg Laughlin, a professor at Santa Cruz, and Eugenio Rivera, who was Greg's former postdoc. But it's all kind of mixed and intermingled, and you'll see a lot of the work here comes from the original, what's called California Carnegie team. So basically, as you go out to a dark sky site at night and look out and see the Milky Way Galaxy out there, I don't think there's anyone among us who hasn't wondered, is there something out there looking back at us, wondering if we're looking back at them? So our Milky Way Galaxy looks something like this. This is our sister galaxy, the Andromeda Nebula, a collection of some 300 billion stars or so. A lot of places to imagine where there might be life forms that are perhaps intelligent. Taking a step back even farther to the Hubble Deep Field, you start counting the stars, and it's some big old number like 70,000 billion or something like that. More than all the grains of sand on all the world's beaches. And so with that kind of perspective, we ask ourselves this question: are we alone? That's the big question that everyone would like to know. At least I would like to know. And it's interesting because it has an answer. And the answer is either yes or no. It's not none of the above. And either way, it doesn't matter. Either way, the answer is utterly profound because it tells us who we are, as Carl Sagan, I think, used to say, calibrates our place in the universe. And so we'd like to know. And we'd like to know not just by thinking about it, but by actually making measurements and seeing if we can get closer to the answer to that question by making measurements. So the universe, as most of you know, is a place of extremes. And to find life of the type that I think we would recognize or understand, namely the kind of life that you could make a hamburger out of, or that could make a hamburger out of you and eat you, you need water. You need the whole organic chemical soup. You need water in there as a catalyst. And so since the universe is a place of extremes, temperature extremes, you're either too close to a star and you're too hot, or you're too far away and you're too cold. Then what we would like to do is try to find that place where water can exist in liquid form on the surface of a planet, say, and exist for long periods of time. Whoop, let's go backwards. Why isn't this going backwards? Yeah, all right. Oh, it's going to be stubborn. Wow. Okay. Well, never mind. So, so far in our searches for life out there, Earth is the only place that has shown evidence of biology. And so we're looking. We look among the planets of our own solar system. Mercury is a kind of a long shot, roasting hot place, hot and dried out. Venus is also a pretty inhospitable place. It's not to say something couldn't live there, but 900 degrees sulfuric acid cloud makes it unlikely that you're going to be making hamburgers there anytime soon. Mars, our sister world, of course, has great possibilities for life, and we're finding all kinds of evidence that there were probably early oceans there and vast quantities of water that have since been locked up onto the surface or have evaporated away. The rover Spirit and Opportunities are looking around trying to find evidence of life. We've got, you know, fluvial valleys going down gullies and such. So there's a lot of indications that there may be subsurface water there. But so far, no organic life. Well, just skip beyond that. So looking farther out in the solar system, Jupiter has a couple of very interesting moons. Io, very volcanic because of its tidal distortions. Europa, probably also heated by tidal distortions. And of course, the surface of Europa has these cracked, what look like cracked ice flow patterns that make us think that the surface is a layer of ice that is floating on a liquid subsurface. And so the models would indicate that we might have a subcrustal ocean in Europa. And of course, it'd be great to go there and try to melt down through the ice and see if something lived down there. And this is, you'll see some renditions from Lynette Cook, who is our space artist that here is thinking about alien life, maybe under Europa ice or who knows what. And so there's a lot of intriguing possibilities, but so far no direct evidence of that. Following the water further on out, we get to Saturn and its main moons, Titan, which of course has a lot of organic things on its surface. The Cassini and Huygens mission has found evidence for lots of organic rivers and lakes of methane and ethane on Titan's surface. More interestingly, I think, in recent times, is the icy moons that have been found. And here's some photographs of some of those. View of the ring's edge on, the shadow on against the planet. And this is one of the moons, Dione, I believe it is. And we think there may be subsurface water there, and we're orbiting, basically looking for these things. I believe this is Enceladus. I'm not a planet scientist person, but it seems to be spewing plumes of what look like icy water. And so there seems to be a growing list of places where we might be able to find liquid water in our own solar system, and that's where we should go to look for life. Going further out, now it's getting pretty cold out to Uranus, a frigid, tilted gas ball. Neptune, even colder, but a lot of water out there. I mean, these are basically water bags. And then out to Pluto, a distant ice world at the edge of our solar system. So if we want to expand our search even farther, we've got to look out among the stars for places where water can exist in liquid form. And following the mantra of follow the water, we want to find places where water can exist in liquid form for a long time, for billions of years, for the sort of time scales that it takes for evolution to work its magic. So this is where the idea of planets in habitable zones around stars come from. Orbits are stable over periods of billions of years, and if you have an orbit that's not too close in and not too far out, just at the right temperature so that any water on the planet could exist in liquid form on or near the surface in the atmosphere, you'd have a place where you could brew up life. And so we'd like to find out how common it is to find such things. So when we look out among the star clouds and the nebulae out in the universe, for example, for Orion, we see a lot of water. We see it in radio telescopes. There's huge amounts being formed here in the Orion Nebula, enough to fill all the Earth's oceans every 24 minutes. There's a lot of water out there. And there's a lot of water and other organic type things in these dust disks. These are protoplanetary disks of the Orion Nebula. And some 80% of young stars have these protoplanetary disks out of which planets form. And we can see that in the infrared and the radio. So the building blocks are out there. And what we'd really like to understand first is how and why do planetary systems form. And you know, we've only had, oh, here we go again. We've only had one system to understand how this works on, and that is our own solar system. And so we'd like to find other cases where other planetary systems have formed to learn how that process works in detail. You can't learn about humans by studying one person. You have to study a whole population. And so we'd like to find a population of planets that we could use to see how nature makes solar systems. And I guess I would say that in recent times, in the last 10 years or so, with the discovery of exoplanet systems, we've had to rewrite the textbooks a number of times. We've learned a lot of things about extrasolar planetary systems in general that we couldn't have guessed from our own solar system. Here we have a young planetary system forming, and we have core accretion going on. We have colliding bodies that eventually grind themselves down and coalesce into larger oligarchs that eventually begin to eat out feeding zones and out beyond the ice line can agglomerate large mantles of water and hydrogen and helium and become the gas giants. So with so many stars out there, the question is, where do you look? I mean, how do you find these systems around the distant stars? Which ones have planets, and how do you track their motions? Well, one of the ways you could think of doing it is just use the Hubble Space Telescope and just do imaging and look real close in for planets. But that's a tough go because planets are so faint compared to their star, and they're so close in that you have the canonical problem of the firefly next to the search lamp. Stars are billions of times brighter than their planet. So the planet is hidden in the glare of the star. And even with the best telescopes, space-based or ground-based, it's really tough to be able to make that kind of a differential detection. So another way is to try to measure the effect that the planet has on the star. And since the planet and the star are actually orbiting one another, the star has a little orbit that it goes through. It's a small orbit because it has a lot more mass than the planet. And that planetary orbit around there will make the star appear to move on the plane of the sky. And if you're lucky and you have the right kind of technology, you could detect that motion on the plane of the sky astrometrically. You could just look at the position of the star with respect to reference stars, and you could see it regularly wobbling, and you'd have an astrometric detection. This was supposed to be the great white hope of NASA, basically, was to use astrometry, space-based astrometry, to do this, but it really hasn't panned out over the years. The other way to do it, one of the other ways to do it, is to detect the motion of the star just along the line of sight, just directly along the line of sight. We call that the radial velocity. And so you're not actually watching it move on the plane of the sky, you're just watching it move towards you and away from you. And we do that using the Doppler effect. We just basically take advantage of the fact that spectral lines shift, and if you can measure those shifts and measure their periodicity, you can tell a lot about the planet that's pulling on the star without actually having to see the planet. So that's what we've been involved with for the last about 22 years or so. There's 3 telescopes, 4 now with Magellan, and this work started in about 1987, and we've been measuring Doppler velocities of nearby stars, large numbers of them, at a Doppler precision of about 3 meters per second for several decades, 22 years at Lick, 13 years at Keck, and about 12 years at the Anglo-Australian telescope. And these kind of time scales get you down, get you out to probing planets that are in orbits at Lick, that are orbits as big as about 8 astronomical units, about 6 here and about 6 here. So it's just a question of the longer you monitor these stars, the larger the area you can probe in terms of finding planets. So you just have to be patient. all this work is done using generally a shell spectrometers, where you collimate the light and you then bounce it off what's called a shell grating here, which is a coarse disperser. We're using a high interference order. That then goes through another set of dispersers, in this case prisms, but it could be another grating, that's at right angles to it. So you actually have two spectrometers that are orthogonal to one another, and then into some kind of a camera that takes all the angles that are encoding the wavelength information and puts them onto a detector. So now you have X and Y position. So now every X and Y position on the CCD corresponds to some known wavelength. And so it's kind of interesting to think about this. We are creatures of carbon, basically, that are crafting devices out of basically sand and steel to collect and sort photons. That's all we're doing here. It's all done with sand. So when you dice up a spectrum in this way, it fits really nicely onto a two-dimensional detector, charge-coupled device, CCD. And so that gives you a very efficient packing of the information onto the CCD. And so that's what's shown here. This is a color-encoded shell spectrum, and you see some familiar things. There's the hydrogen Balmer line, H-alpha, sodium D lines there, magnesium triplet, and lots of, all the chemical elements are down in here, iron, chromium, manganese, nickel, all those common elements. And we don't really care what the lines are. All we care is how they move. So when the star is orbited by its planet, it makes all the lines move systematically to the left and to the right, to the blue and to the red. Stars coming towards you, everything moves to the blue. Stars going away, they move to the red. And to first order, all these lines move the same. It's actually much more complicated than that, but pretty much it's kind of, they all shift to the left, they all shift to the right. And you have a lot of lines, so you're going to try to measure that shift. The problem is the shift is very small. This is a typical 2K by 2K 2048 by 2048 CCD, and the shifts that we're dealing with are like 1,000th of 1 pixel. They're very small. So calibration becomes a difficult issue. And as an example, the size of the effect, what I like to use as an analogy, is imagine a 6-inch long wooden or steel ruler. And you lay it down on a table, and you measure its length with a set of really accurate calipers. And if you've made your ruler right, it's 6 with as many zeros as you like after it, inches in length. Now you take that same ruler and you balance it on its end. And now it's standing up, and now you measure its length again. It's going to be a little shorter. And it's going to be shorter because it shrank under its own weight, right? That's how you feel at the end of the day. You're kind of a little shorter. You know, in the morning, you're real tall. It's just gravity, basically, is compressing it under its own weight. And that's the size of the effect. Oh. That's the size of the effect that we're trying to measure. About a part in 100 million, something like that, part in 10 to the 8. So looking for planets around stars, say you have 1,000 stars in your target list, is like walking into a room that has 1,000 identical rulers laying on the floor. And some of them, some small fraction, maybe a few percent, 5%, 10%, are changing their lengths by that kind of size scale on periods that you don't know. So you have to measure them all, then you have to come back and measure them all again, and just keep doing this week after week, month after month, year after year, to find out which ones are changing and on what time scale. The problem, of course, is you can't pick one of these up with your fingers, because the heat from your fingers will make the ruler expand by about 60 times the size of that effect. So you have a real difficult calibration issue going on here, because your spectrograph, your telescope, and your spectrometer is basically a ruler. And nothing that we make is stable to those levels. I mean, the changes in temperature, humidity, pressure, all those things make anything made out of glass and metal change its calibration. So this has been a problem, and the solution to this was something that Jeff and Paul came up with, was to impress the calibration on the starlight before it gets into the spectrometer. And that's what this is for. This is an iodine cell. And it's a bottle about the size of a beer can, Pyrex, usually made of Pyrex. You get a glass blower to make it. And you basically take it and you get the glass blower to make it, and it has a kind of a feed tube down on the bottom there. And you clean out the inside to an atomic level of cleanliness with all kinds of nasty acids. And then when it's all entirely clean, you drop a little speck of iodine in there, a little crystalline speck of iodine, just like what you'd get off the lip of your iodine bottle in the medicine cabinet, but chemically pure, isotopically pure. And then you suck out all the air and have the glass blower seal it off, and now you've got iodine trapped in there. And then when you heat this up to above 35 centigrade, the iodine sublimes into this light purplish gas that you can see there. And that gas has a very rich spectrum. Here's the iodine line, or iodine in front of the spectrograph slit here, which shows the light coming down from the telescope and through the iodine cells, got a heater wrapped around there to heat it up, and then down entering the spectrograph at that point there. So we impress this absorption spectrum on the stellar beam before it gets into the spectrometer. So here's a kind of a crummy CCD, a shell spectrum of iodine showing thousands and thousands of lines. This iodine, these I2 molecules have a huge number of transitions in the optical region of the spectrum. And this is going to be superimposed on the stellar spectrum. And we're going to measure all of our shifts with respect to these iodine lines. So here's just a very small piece of one of those orders. This is about 4 angstroms of spectrum showing the richness of the iodine, the lines, these real deep lines here, as compared with stellar lines. And so we're going to model that interaction, basically. And the answer that we're looking for is what the shift is of our stellar lines with respect to those iodine lines. So here's what the sun would look like from a distance using this technique. With 3 meters a second precision, we would see the sun being yanked around like this. And what you see, of course, is there's a periodic thing going on here with an amplitude, semi-amplitude of about 12 meters a second. That's Jupiter tugging on the sun. So there's a period of about 11 or 12 years right there, the period of Jupiter. There's also a longer period due to Saturn right there. So in 70 years, easily, probably even half that time, you could tell that there were Jupiter and Saturn mass planets pulling on the sun, and you would be able to measure their periods as well, and maybe even the shapes of their orbits. Here is one of the early planets to show you how this works. This is 16 Cygni b. It turns out to be a very eccentric planet. And this is the typical radial velocity data that we end up getting. So we plot the velocity here in meters a second versus time. And each one of these points comes from an observing run, from a night, basically. And we don't measure absolute velocities. We only measure changes in velocity. So the 0 is arbitrary. We usually put that at the mean of all the points. And we're just measuring accelerations, essentially. And so the first thing that comes out of this kind of a data set is the period, of course. So you fit a Keplerian. This curve is actually a Keplerian curve fit through here. In this case, the period is 2.2 years. And then using Kepler's third law, p squared is proportional to a cubed. It gives you the size of the planet's orbit. The second thing that comes out is the amplitude of the velocity wobble. And in this case, the larger the amplitude, the more massive the planet is. It's like if you're looking at somebody in a park and they're taking their dog for a walk and you're a long ways away, you can kind of tell how massive the dog is by how hard he's pulling the human around on the leash. So it's the same thing here. The planet's pulling the star around, and the more massive the planet, the larger this velocity wobble is. And that then leads to the mass of the planet. It's actually a lower limit on the mass of the planet because we don't know the tilt of the planetary system. So there's a sign of inclination involved there, and it gives you a lower limit to the mass of the planet unless you can find the inclination in another way. The third thing you get is that the curve is not sinusoidal. So there's actually a very sawtooth pattern going on here where it drops rapidly and then climbs more slowly, drops rapidly. And that gives you the shape of the orbit. In this case, it's a very eccentric orbit, about 0.68. We have orbits that go all the way up to, I think, about 0.98 eccentricity, wild orbits. So you get the period, the size of the amplitude wobble, which gives you the mass, and we get the eccentricity. All three of those come out of that. And you get the goodness of fit here, which tells you whether there's anything else hiding in there or not. If you really know your errors, you can use your RMS fit to tell you whether there's more things in there. So this is what 16 Cygni b would look like if you projected its orbit down on our solar system. And it's kind of wild. It's got a big eccentric orbit, so it swoops in within the orbit of Venus and then swoops out way beyond the orbit of Mars. So it's kind of a bizarre thing, pretty good size, good mass planet. And a lot of them are like that. These are crazy, we call them killer Jupiters, basically. Here's the first example of a multiple planet system. And the idea is you're observing along for a while here for a couple of years like this. You get some data. And the way we search for planets is we do a power spectrum. So for a bunch of different periods, we just go along here. At each period, we say, what is the amplitude or the power in a sine wave that would fit this? And at most of the periods, the sine wave doesn't fit very well, but at one period it fits really well. And so that spike right there tells you that there's probably a periodic signal in that data that is very well fit by a sine wave with a period of 4.61 days. There may also be something at that period, or that period, or that period, or that period, any one of these other peaks. So this was how you found the first planet. Was a very hot Jupiter, a close-in hot Jupiter. And you wonder whether there's other things in there from these other peaks. So you go and you get more data. So as the years go by, you get more data. And you can see we had pretty big error bars at first, but once we began to see there was something going on in there, we began to hit it more intensely, and we began to drive our error bars down. So we were really pounding on it after a while once we found more and more things in there. So you fit that with a power spectrum, and then you remove that 4.61 day signal, and this is the residuals. This is what's left after you remove that known 4.61 day planet. And what it may look like noise, it shows that there's 2 more planets in there. And this is them. There they are. There's a long period guy there, and then there's a short period guy. So there's actually 3 planets in here, and we're pretty much fitting almost every point. Chi-squareds down to very close to 1. So this system now actually has 3 planets in it. It has a 4 Jupiter mass with a 4-year period and a 2 Jupiter mass with a little bit less than a 1-year period. And then it has the close-in guy down here at 4 days. And once you get to that point, then you pass it off to the theorist, and they can try to figure out how this thing got into the configuration that it's in. In this case, there's a secular resonance going on, and so they have a lot of fun with that. So that's a multiple planet system. Now with all these systems, we don't really have a way to see them, but fortunately we have Lynette Cook. And so we tell Lynette Cook, draw us a picture of it so we can use it for the public, right? And, you know, I'm sorry to say they mostly end up looking like Jupiter and Saturn. You know, it's not too surprising. But she has her own little artistic flair once in a while. She can go through phases where she wants to put moons in there that are volcanic, or they have water or ice or whatever. In this case, she didn't have any foreground moons, but you can see the outer guy, and then the middle guy, and then the way down in there is the inner one. And we try to get the perspective right, and you know, it's space art. What can I say? Fun stuff. So this is one of the most interesting objects that we found years ago, is 10 years ago now, HD 209458. This is the first transiting planet. And up until that time, there were a number of very vocal naysayers that said, you guys aren't seeing planets at all. You're seeing waves on the surface of the star. These are non-radial oscillation, tsunamis, P-mode oscillations, whatever you like. It has nothing to do with planets at all. And it was really quite a hindrance to the field. I remember in particular, I was getting, our group was getting problems with time assignment committees that were saying, well, what about this person who said this and that and the other thing? And I think we even lost some funding due to some of that naysaying. And you know, it's good to be a devil's advocate, but it was kind of getting out of hand. And we had no way to really prove that we were seeing planets. We were just seeing, you know, wobbles, basically. We thought we were seeing wobbles. So on Friday, November 5th, we were out at Keck Observatory, and I think Jeff was exercising a software routine which sniffs through the data structures looking for periodicity. And he was training it and just kind of trying to optimize it. And it came across this system that I think it had 9 points in it, and it found a good sine wave fit with a period of 3.5 days. Pretty big amplitude, 81 meters a second. That's a huge amplitude for us. And it fit quite well with an eccentricity of 0. Now, we had known at that point that all short period planets had eccentricities of 0. It's easy to fit 9 data points with a sine wave, particularly if you make the sine wave have eccentricity and not be sinusoidal. You can find any period that'll do that. But it came out to be 0. And so we thought, well, maybe this is real. Maybe it's a short period planet. So we thought we'd look a little closer. So the thing about short period planets is that on average about 10% of short period planets, periods in the 3 to 5 day range, will show transits. Nature will have thrown you a bone, and you'll happen to be close enough to the plane of the orbit where at some point you see the planet go right across the disk of the star. And when that happens, you'll get a little drop in light, about 1% or 1.5%, something like that. So we thought, well, okay, maybe this will show a transit. And we had done this 4 or 5 times in the past, each time thinking maybe it will show a transit. and passing it off to a photometry guy and saying, go look at this time and see when the thing comes across, see if there's a transit. And each time there was nothing found. So we knew we were due. It takes about 2,000 stars actually to find one of these things, and we were at the point where we needed to find one. And so we made a prediction. And the prediction was that 2 days later, I think Sunday night I think it was, that was when the next transit would occur. And so we made this prediction, and given the accuracy that which we had the orbit, we had about a 2-hour window where we predicted that the light would go down. And so we handed this off to our collaborator Greg Henry, who fired up his automated photometric telescopes, and this is the data as it came in that Sunday night. And just at the right time, down it went. And then it set. So we got ingress, but we didn't get egress. I mean, it literally set. It was just too low on the horizon. But that was good enough. I mean, at that point, we knew we had the first transiting planet. So we had Lynette Cook all ready to go. Jeff had her all fired up. And there it was. This was the graphic that came out. And it was interesting. We got a lot of editors of magazines and newspapers and such that were just amazed at the mighty imaging capability of the Keck telescope. It could see such fine detail on the stars and galaxy in the background. Just amazing. So I think Lynette did her job very well there. What we're trying to show here in this is the size of the planet relative to the size of the star. That's accurate. And also the position of where the planet comes across is accurate. So keep in mind what you're seeing here is a shadow that's cast by this planet 153 light years across space that is sweeping by the Earth. It takes about 3 hours to go by any place on the Earth. So this is happening, of course, all the time. It's just hard to know when it's happening, where to be pointing and looking for that percent dip. So the other thing we're trying to show is this light blue glow around the edge of the planet there. Because once we got that first transit, we immediately realized, of course, that you could do spectroscopy on the atmosphere of the planet. You take a high-resolution spectrum when the planet is in transit, another one when it's out of transit, and either take the difference or the ratio of those, and that will tell you the spectrum of the light that made it through that little blue region right there. And that has been done, actually, from space. Dave Charbonneau and Tim Brown managed to do that. We had a similar ground-based confirmation. And you can see sodium. You can see the sodium D line strengthen due to light passing through the atmosphere of the planet. And this will be a growing industry in years to come. It's hard to do. It's a part in 10 to the 4th, so you need quite high signal and noise to do this, but it is quite achievable. And it'll be fun in the future to find more of these bright transiting systems and begin to do more spectroscopy in the optical and in the infrared. So this has become a whole industry in its own right, the spectroscopy of transiting planets, not only as they pass in front of the star, but as they go around behind the star as well, and looking at spectra on from the light that is just emerging from the planet by itself rather than being occulted.
So what's the mass of the planet?
The mass of that planet? This is about 60% of the mass of Jupiter, but it's about 40% bigger than Jupiter. So it's a puffed up planet. I mean, the thing I didn't point out here, because I'm just kind of running short on time, was that once you have, of course you can all imagine, once you have the radius of the planet, and now you have the mass, because you don't have a problem with inclination. You know the inclination now. If you have mass and radius, you have the density, right? So you can tell whether it's a rock or a gas bag. And to nobody's surprise, it was a gas bag, but it was an inflated gas bag. And I think one of the most important things of this result was it showed, the theorists were able to show pretty quickly that this planet could not have formed in this close. It's being heated by solar insolation, by tidal effects, but it could not have formed in this close. It had to form out farther and then migrate in. So this is first real proof that planets migrate. And it migrated in there and then parked in this orbit. I don't think we really understand what it is that makes these things park in the orbits that they're in. Maybe a lot of them don't, and they fall in. But this one is parked and pretty securely in that place, and planets do migrate. Okay, well, so in the last 10 years or so, we found lots of planets. We used to do diagrams like this, but they got too crowded, so it gets hard to do it. There's over 400 known planets now, and I guess the takeaway message is that planetary systems turned out to be much more diverse than anyone had guessed. And our own solar system was not a very good model for the kinds of things that are out there. I'm not going to talk in detail about the properties of extrasolar planets. It's a little bit dry, I think, for this kind of a venue. But I'm going to tell you about where we're going, where we've been and where we're going. So this is a plot of discovery space where we're plotting the mass of the planet, logarithmic mass in Earth masses, and the size of the orbit, logarithmic size of the orbit. And this is, it's a little bit of a dated slide. There's more dots on there now. There's probably only about 100 dots in there. But there's two areas of interest to us. One is for orbits that are bigger than an AU, out at 2, 3, 5 AUs, orbits that would remind you of Jupiter or Saturn. And to probe that area and understand what kind of population of planets is out there, it just takes time. Because you have to see a planet go through its full cycle before you can really claim that you've got the orbit. And so, for example, for Jupiter, you have to observe it for 12 years. You can't hurry it. So you just have to hold your precision and just keep on the star for a decade. Saturn even longer, several decades. So that takes time, and that will just come as time goes by. The other area is very low mass planets, and that we can hurry, that we can do sooner, but it's difficult because you need very high precision. And so this is getting down to planets that have masses of 1 to 10 Earth masses, things that you could actually walk on. You could stand up and walk around on, that have a surface, an actual solid surface. So pushing to these Earth mass planets requires improvements in our original precision. We were originally at 20, 30 meters a second, and we fought our way down to 10, and we fought our way down to 3, but that's not good enough. You've got to get down below 1, basically, if you want to do this. And we were stuck at 3 meters a second with the spectrometer that we're using. It's called high-res, out at Keck Observatory. And so we realized that it was due to a lot of very subtle effects in the CCD and in the signal processing. So in 2004, we put in a new focal plane of 3 CCDs. These are each MIT Lincoln Lab CCDs, 2K by 4Ks, all parafocalized onto a big focal plane. And this thing was about $1 million upgrade. Each of these is about $100,000. If you can't even really buy them. They were part of a consortium. But that upgrade got us from a precision of worse than 3 meters a second down to less than 1 meter a second in 2004. So now we finally had the precision to really go after these things. Oh, come back. At that level, when you're down below 1 meter a second, you're tracking the motion of the spectrum on the CCD at a level of about 80 atoms on the silicon lattice, from, you know, summer to winter, spring to fall, year to year. So it's just insane. I never would have believed we could do that, but that's what's happening. And it's because there's a lot of lines, and we're doing some very sophisticated modeling to do that. I haven't gone into any detail on the modeling. That's a little too arcane for this. Anyway, so once we had that extra precision, we went back to one of our favorite stars, Gliese 876. This is a late type M dwarf, very nearby, only 15 light years away. You could easily have a conversation with it if there's somebody living out there. And this is one of Lynette Cook's renditions that shows we knew there was a 60-day and a 30-day Jupiter going around this. They're in a 2-to-1 mean motion resonance. And in fact, they're massive enough that they're actually gravitationally interacting so that their orbits precess and they change on time scales of a few years. So over a few-year time scale, you can sense those interactions and actually derive the true mass, the actual strength of gravity that's happening in the system. And up until that point, we had been monitoring this thing, and we had pretty good fits to the data. In fact, up until this point right here, about all this stuff here, we only knew that there was a 60-day planet. But suddenly when it began to do weird things in there, we suddenly realized that there was a 30-day hiding in there as well. Nature was very unkind to us, hiding it at half the period there. But once we figured that there were 2 in there, then we began tracking it better. And we could see that our fits were not as good as they should be. There was something else was missing in there. Quite a bit of precession in the orbits, the outer guy, 40 degrees per year. And so we went back, got a new template, and we really started pounding away on the thing. And what came out of that, if you look at this as color-coded years, 1997 to 2004, so about 7 years worth of evolution here, you can see how this orbit evolves, and you see how Gliese 876c orbit evolves. And so we had to model this with a 3-body model. So we had the star and 2 planets gravitationally interacting with one another. And out of that modeling came 2 things. The inclination of the system, because you know the strength of gravity, and another planet. And there was another planet at a very short period, about 1.9 days, a 3rd planet emerged, and this was a 7.5 Earth mass planet. And there's no Sinai in there anymore. This was the first probably likely rocky planet or close to rocky planet. A little hot though. I mean, it's kind of a hot rock, but it's because it's only got a period of 1.9 days. It's almost right down there in the star. Probably a circular orbit, semi-amplitude of about 6 meters a second, and that's what it was. Still not getting perfectly good fits here. I mean, that should be down more like around 2, but you know, we're getting there. And so then this was an NSF prepared graphic of flying into this system. So we're gonna fly into this past the 60-day and then past the 30-day. There goes the 60-day. This is your tax dollar hard at work here. We didn't pay for this actually. And then you get in real close, and tucked up in there real close is that 1.9 day super Earth. We'd call it super Earth. Well, that is our attempt to indicate that this planet is undergoing tidal heating from both the star and the other planets. So there's probably a fair amount of internal heating on top of what the star produces. So on the dark side, we're trying to show it's probably got some volcanic stuff going on inside it. On the bright side, it probably also has a very extensive atmosphere. Could be a very thick atmosphere. We don't know how thick it could be, but likely it has a very extensive atmosphere. So we're kind of trying to show both of these things in this artist's rendition. So it's about 73% bigger than the Earth, 7 Earth masses, something like that, in a very tight orbit, pretty hot, 400 to 600 K, kind of intermediate between a hot Neptune and a true terrestrial planet. But now we're finally down in the area of rocks, and this is a very common star. I mean 95% of stars are like this, and it's got rocks around it, hot rocks. Well, that's pretty good news. It's like, wow, okay, good. There must be a lot of them out there. The other thing that's kind of fun about this, you know, when you're on a cloudy observing night, you're dreaming about all sorts of things. You think about a planet like this, it's tidally locked to the star. So one side is always facing the star, and the other side is always facing away. So the hot side's about 370 centigrade, and the cold side's about minus 100 centigrade. But somewhere in between, right, it's got to be sort of habitable, right? There's sort of a habitable thing there, right? So you got blasted desert out there and frigid cold there. And this is kind of an artist's rendition that maybe shows sort of a band where it could be in some way habitable. Now, of course, there's probably hellacious winds being driven around in this thing, and I don't pretend to think that, that there's actually something there. But imagine in that habitable band there, deep chasms. You know, who knows what kind of stuff nature and life is brewing up in the muck that's down in these canyons there, with the winds howling overhead and the lightning flashing, making, you know, all kinds of organic molecules and precursors of life and such. So it's kind of fun to think of that maybe there are celestial abodes where life has managed to gain a foothold. Anyway, so looking at our galaxy now as a whole, the planets of the Milky Way Galaxy, there's about 200 billion suns in our galaxy. Some would say 3 or 4 times that many. We don't really know, but there's at least a few hundred billion. We know that. And we know from our surveys now of probably 2,000 to 3,000 stars that the various teams of the Earth have been monitoring, our team, the Swiss team, and others, that at least 30% of the stars we survey, and these are basically late F, G, K, and M stars, have detectable planets. We found planets around at least 30% of these. And they're Jupiters, Saturns, even lower mass things. Some would say, the Swiss are now saying they think it's even 50%. They're pushing that number up every day as we speak. So there's a lot of planets out there. So you're talking about 60 billion planetary systems at least out there in our own Milky Way. It's kind of a staggering number when you think about it. And they're mostly Jupiters and Saturns and Neptunes, maybe some super Earths, hard to know yet. But what you really like to do, of all these 400 currently known nearby systems, you'd like to find the ones that maybe harbor habitable Earths. And currently most of them aren't known to harbor habitable Earths. They have these killer Jupiters in them. So we'd like to go after the water world. We want to go after something that reminds us of our own, a terrestrial mass or few terrestrial mass planet in a habitable zone. Not too close in, not too far out, that water can exist in liquid form between 0 and 100 centigrade for long periods of time. So you think a lot about how do you find Earth-like planets around nearby stars. I'm not talking about stars that are long ways away. I'm talking about stars that are very near to us. And I think it all comes down to cadence. It pretty much comes down to cadence. And that's what the APF provides. And the APF is called the Automated Planet Finder. And this is being built, it's almost finished now, atop Lick Observatory. It's right next to the astrograph. There's the front of Lick Observatory in Silicon Valley down there. And this is a 2.4 meter, eventually fully automated telescope that is entirely devoted to radial velocity work. The problem is that the work we do out at Keck, we can't get enough observing time to get adequate cadence. We just can't. I mean, it's a shared facility. So we managed to get a hold of funding through a congressman, basically, and get this project on the Defense Department budget the year that 9/11 happened. And when George Bush signed the budget after 9/11, this was in the budget. One California planet finding telescope, $6 million. And it was right in there amongst the 20 stealth bombers and 400 Bradley fighting vehicles was one California planet finding telescope. So suddenly we had $6 million to build this thing. So it's actually taken 7 years to do this, I'm ashamed to say. But it's now finally coming together. It's a beautiful little telescope, 2.4 meters, and it's optimized specifically for planet finding. So I used a very small secondary mirror. I mean, why block photons, right? You don't need fields, so make your secondary as small as possible so you don't block photons. And use silver secondary and tertiary mirrors. I'd make the primary silver as well, but we don't know how to do mirrors that big in silver yet. Here's a picture of the primary mirror. This is the guy who's the sort of the Wizard of Oz in the background here, Dave Anderson at Rayleigh Optical, who figured it. This is our optician, Dave Hilliard. And here we are, carbon-based life forms, again assembling silicon and sand into telescopes so we can sort and count photons. And that was finished in 2008, about a year ago. And then it was brought to the company that made it, EOS, in Tucson, where it was integrated into a very nice, short, stubby, essentially satellite tracking telescope. And the mirror is in there with a layer of protective coating on it there. Slews pretty fast, very accurate, points to about an arc-second accuracy all sky. So it's a good robotic facility that you won't need an astronomer to sit there and make decisions about if you have a good mature target list. The other thing about this is that I've built a very specialized spectrometer for this that's really highly efficient and specifically suited for radial velocity work. So it's our high-resolution spectrometer that sits over at the Naismith platform where gravity does not vary. I hate variable gravity when you're trying to use instruments. So gravity maintains a fixed vector over there, so you don't have to deal with shifting gravity vectors. It has a very highly efficient optical train. You basically go through an iodine cell, has atmospheric dispersion compensators, as a collimator that also serves as a camera. You go through it forward, through a prism, often a shell, a very steep a shell, back through the same prism, back through this system and off to a CCD over there. So it's a very compact, all dioptric system that is very efficient. It's held together with a space frame that's an intelligent space frame that is designed with different materials in the various struts that allow the optics to basically change to piston basically with temperature so that you maintain focus and scale over huge temperature ranges. So it's a passively athermalized space frame. And that cost about $2 million, and I was able to get that money from NASA at the last minute to put this together. Part of the trick in making this efficient is that we had to learn how to do our own coatings. So we learned how to make spun sol gel AR coatings, and here's one of the lenses in there being spun with a funnel full of sol gel. It just drops on there, and then at about 30 seconds it just turns into this beautiful AR coating that is fairly soft but is quite broadband. We also learned how to dip, so here's a prism being dipped in a dip tank, and by just drawing it up at a very uniform rate you create an anti-reflection coating layer on there. So we had to learn how to do all this. We're in a little clean room thing that we built there. We also have a few mirrors in the system. This is the kind of mirrors that we develop basically. This is 100% reflection here. This is 80% down here. So a typical aluminum mirror would be down around 90% if you're lucky. This is basically a perfect mirror from about 340 nanometers all the way up to beyond the range of silicon. It's even making some light up there. We're producing light up there. It's probably this light over here is appearing over there. You can almost count the layers in. You can see this is a multi-layer mirror. This is about 151 layers It's essentially a perfect mirror. I don't know that anyone's ever used such a thing in astronomy. This is a small one. You can actually buy these for about $1,000. But we actually ended up making about an 8-inch diameter one as well from a company called MLD over in Silicon Valley here. I'm very proud of it. We should publish a paper on it. It's an amazing, amazing mirror. So this is a view from the western side of Lick, looking back at the 3-meter telescope. And there's the APF over there, a little dinky little APF there. But the fact of the matter is that the APF is going to outperform the Lick Observatory facility, the 3-meter telescope, even though it's a smaller telescope, because we have such a highly efficient spectrometer on there. It'll beat the 3-meter by about a factor of 4. So less is more there, hopefully. So this is a simulation of what the telescope will be able to do in the first 6 months. We have a hypothetical planet of about 2 Earth masses that we put around a star. And the star is about a half a solar mass, so it's basically an M star. And we're hitting it essentially every night. And this is the radial velocity data that comes out. And there's the power spectrum. And we put in a planet at a period of about 50 days. And out it comes in the power spectrum. Easy detection to make. So we'll be able to find, you know, super Earths, 1 Earth, 2 Earth mass planets within less than a year, basically, once this thing gets underway. And it's all because of that dedicated cadence that makes that possible. And this would be a temperature of about 80 degrees centigrade. This would be a habitable planet, basically. So I'll just give you a couple of quickies about some things that are emerging now. We have about 1,500 stars in our program, and so we have a thing called the Codex, which is essentially 77,000 numbers arranged in 1,550 rows by about 50 or more columns. And this is everything we know about all the stars in our program. 1 row for each star all the way down, and all these columns are everything we know about the star. And it's a dynamic database. It knows about how many observations you have, when the last time you observed the star was, what kind of power it sniffs in the data at various periods, whether it sees 1, 2, or 3 planets in there. Comments that we use when we're at the telescope to remind us which stars are important or not. And so here's one that's going to come out next week. Actually, I have a press release that hopefully will come out on Monday that's going to show a very nearby star. This is a solar twin. This is about as identical as you can get to the sun. 8.5 parsecs, about 27 light years away, a star called 61 Ver. And this thing has been a very heavily studied star for many years. A lot of astrobiologists will tell you it's one of the most interesting stars in the sky for various reasons. And this is our radial velocity data set. We've been following this thing for about 4 years. The blue points are from the AAT telescope, and the green points are from Keck. You can't really see the points. They're kind of buried in it. And that line there is the fit, Keplerian fit to that. There's at least 3, probably 5 planets in this system. So this is the successive periodograms of how we fit those out. This is a full periodogram of all the data. So you go and fit that 38-day planet out of there first. And when you do that, the residuals, their power spectrum is this thing. And it shows a peak at 4 days and another one at 120. We usually go for the long period guy next, but it doesn't matter. You can do them in either order in this case. So you fit the 120-day planet next, and then there's the residuals as that one. And then you fit the 4-day, and then a 380-day, and then there's an 80-day, and then there's probably other stuff too. And as time goes by, we'll see more and more peaks coming out of there. So the interesting thing about this one is that this 4-day is another one of these 5 Earth mass things. So there's another hot rock down in there. And what gives you even more kinship with the solar system, our own solar system, is that Spitzer has detected a dust disk around this thing at about 100 to 200 AU. So it's like, you know, twice as big as the orbit of Pluto or so. But the 70 micron infrared excesses means that there's material out there, cometary material, that's grinding itself up into this like a Kuiper belt sort of thing. So it reminds us a lot of our own solar system. It's very nearby, looks just like the sun, and it's packed with planets. So that's kind of fun. And there's the kind of a bird's eye view of the system. Here's another one. This is going to be in the same press release. This is a G0 star, a little bit farther away, about 75 light years away. Almost a naked eye star. It's about 6.5 magnitude. If you still have your night vision in a dark sky, you could probably see it. This is the radial velocity data here. And this is our fits, basically. And there's 3 things in there. There's a 7 Earth mass planet, with a semi-amplitude of only about 2 meters a second. So we're really getting down here now into the muck. 6-day period. Then there's something that's like a big Neptune at about 446 days, kind of like the Earth's orbit, a little bit bigger. And then there's something much closer to a Saturn at about 14 years in there. So the takeaway from this is that the nearby stars, and you don't need M dwarfs, these are G stars like the Sun, they're full of planets. There's a lot of planets out there, and they're right in our backyard. So what you'd like to do, what I began to realize a number of years ago, was that if you want to know what the incidence of habitable planets is around stars, you've got to try to find the nearest habitable planet. So here's a kind of a map of the nearest stars out to about 50 light years or so. There's maybe 1,000 stars or so. And within about 30 or 35 light years, there's about 300 stars. And these are stars that we're beginning to look at very closely. That's sort of a target list that you can actually manage. And if you found within that volume-limited sphere a habitable system, that could tell you something very interesting about a parameter called eta Earth. Eta Earth is the fraction of stars in our galaxy, or local stars if you like, that harbor potentially habitable planets. So you could imagine if you found, say, one system around Gliese something or other there, that you could use that to tell you something about what eta Earth was. You could set a lower limit on it. Well, we have such a case, and I didn't want to show it today because we're still working hard on it, but we're hopeful that it will come out. And of course, there's actually 2 habitable systems in there, right? There's that, and then there's us, right? Our own solar system is a habitable system, right? So we can sort of play some fun tricks with this. So eta Earth is this parameter of the number of, the fraction of systems that have habitable Earths, based on the detection of a habitable planet around a Gliese star that I can't tell you about at this distance. And maybe I didn't even tell you the right distance, just to protect the innocent. But it's some distance, right? It's some nearby distance. So if the distance is 33 light years, 320 stars within 33 light years. That's the distance of this thing that's at. 2 habitable systems in there, us and this thing. So eta Earth is, in a statistical sense, unless you're lucky, it's at least 2 out of 320, or about 0.5%. But about 15% of these stars will be at high inclinations or low inclinations. They'll be basically pole on. And when they get close to pole on, you can't detect their radial velocity anymore because there's no line of sight. It becomes undetectable above the stellar jitter. So you put in a correction for that. So now eta Earth's up to about 0.7%. But it turns out, if you look at the Swiss survey and our survey, only about 35 of these 320 stars have been under precision survey with enough radial velocity precision and enough time to be able to detect planets that are down around less than 10 Earth masses. So again, if we're a statistically representative sample, you can correct for that. Eta Earth becomes 0.7% times about 10. So it becomes about 7% or greater. So the conclusion is that either we're really lucky that we found, you know, this gold coin right next to us here on the beach, or eta Earth is at least 7%, and if it's that big or bigger, the galaxy must be full of these things. So the takeaway message here is, if you want to get a good estimate of eta Earth, you've got to look real hard among the closest stars and do a volume limited sample and try to get a fair number of planets found around the nearest stars, and that will give you a good lower limit on eta Earth, and that's what we're working very hard on doing. So we've only explored a very small part of the galaxy, of course, so far. It's just a very small region around us, and so the sky's the limit looking out to even farther distances, and who knows what we'll find out there. There's plenty of stars to search from locally. Here's Lynette Cook in her aliens stage, showing her idea of what may be aliens everywhere. Who knows what'll happen? But you know, certainly it's certainly true that there's a lot of planets out there, and there's probably a lot of habitable planets as well. We're talking about tens, if not hundreds of billions of likely habitable planets. So the next thing, of course, you do if you find one of these things is you become a radio astronomer. So I'm sure I'll have to have a career change. As soon as we find one of these, I'm going to be knocking on the door asking for a job over here, and I'll need somebody to teach me how to be a radio astronomer. I'll put my Jodie Foster earphones on, and we'll all sit and we'll just listen to this thing really, really hard. and we'll watch for lasers, and we'll try to catch dream waves or whatever we can from the thing to start talking about it, start talking to it. So the top 10 questions of an alien. Seth probably has his own list over there. I shouldn't have shown this slide here because you guys are all much better at this than I am. But it was meant to inspire some people at the Optical Society of America, actually. And so when you actually Google this sort of thing, you figure it's going to tell you a lot about the human condition, about human thought. So you say, what are top 10 questions for the alien? I was a little disappointed. All you got were things like, what do women want? And what's the price of gas over there? A couple of years ago, that was a big one, But, these are the kind of things that really kind of begin to get your soul thinking. What is your concept of God, if you have one? What is your cosmology? Are there others out there? For example, can you travel among the stars? And, you hope it's more than just yes or no. Give us some detail. Is your life form carbon-based with DNA? What is the origin of life? Can life achieve immortality? Who knows what? I mean, it goes on from there. These questions tell us about ourselves more than anything. That's why they're so fun to think about, whether we ever detect anything or not. So anyway, it brings me to the answer to our question, are we alone? Well, I can't answer that yet, but I can tell you that there's many solar systems out there, at least 60 billion in our galaxy alone. We know that now. Over 400 now known nearby. Most of them have killer Jupiters in them, eccentric orbits that would toss an Earth out. So the bad news is that about 20% of these have such systems. The good news is that up to about 80% of them don't have these systems. And those are places where we expect to find habitable Earths around a lot of them. We've already found very similar true Jupiter analogs pretty nearby, things that have Jupiters in basically 12-year periods with circular orbits. And I think we're within probably even 1 to 2 years now, certainly not more than 3 to 4, of finding habitable planets around the nearest stars. So stay tuned. We're working on it. Starry nights at Lick Observatory, and that's really just the beginning, not the end. Thank you.
Start with the first question. You started surveying, was it 1,300 stars when you started? How did you first come up with that list of stars?
The original program only had about 100 stars on it at Lick. And these were picked basically as being main sequence stars that are later than the sun and are fairly quiet, that are quiet in a radial velocity sense, that are older stars, that don't have a lot of flares and magnetic activity on their surface. Also stars that were bright. So brightness, lack of activity, old age, lack of being a double star, so that you didn't have 2 stars on the slit. That was how they originally detected. But then the list began to grow rapidly after that. When we opened up the Keck part of it, we added another 300 or 400 almost immediately, and then with AAT we had another 300. Pretty quickly we were up to over 1,000, and now we're at about 1,500, something like that.
And how many will be added by the ATF?
That will not do too many. The APF is, since it's a small telescope and it's designed for real high cadence, what we'll do is we will take very highly vetted stars from the Keck survey or the AAT survey if they're north enough in declination, and we will take candidates that have already proven that they're intrinsically very quiet, but they're a little bit noisier than they should be, because we know how noisy a star should be, and we measure how noisy it is, and if it looks a little noisier than it should be, but it's pretty quiet intrinsically, we think they're probably low-mass planets around it, and those are ones we would feed to the APF. So we might have a few dozens on the APF list. It'll be a much smaller list that will be hit very hard. And we might only do a few dozen stars a night on APF, where we would do 100 or more a night at Keck.
Why did you build at Lick as opposed to other sites?
Why did we build there?
Yeah, why did you build at Lick?
Oh, the APF?
Yeah.
Largely because it was a site under our control. We have the infrastructure there. And we thought about putting it out at Keck in Hawaii or at some other site. But a large part of the expense of such a facility is just keeping it running and keeping eyes on it. And we have those eyes at Lick already. So the 3-meter operator will keep an eye on this thing, and if something's weird, it can go, they can go intervene. So having those people, the crew around, and having the land already there, free power, basically, the infrastructure, was really an important thing. And it's a good enough site for this kind of work. We don't, you know, the night sky doesn't bother us. The brightness of the night sky doesn't bother us.
The Swiss group that's using the HARP spectrograph always emphasize that their spectrograph, for example, is rarely open. They rarely do anything to it, and it's sealed and temperature controlled. Do you have the same sort of setup, or?
We will with the APF, fortunately, because we have the luxury there that it will only be used by us. So it has no moving parts, and it's closed, basically. It's not evacuated like the HARPS facility is, but it is passively thermally stabilized. At Keck, we don't have that luxury. The high-res spectrograph at Keck is a public facility that is used by a lot of different people. We have people in monkey suits that walk in and out and change gratings, that sort of thing. Both the Eschel and the cross disperser have to point to different directions depending on whether you're working on the blue or the red. So we don't have that capability with Keck or with the AAT to do that. It would be nice if we could stabilize it at that level. And the Swiss have proven that that kind of stability has a lot of advantages. It's a lot of cost, but when you have a dedicated instrument like that, it's a really good thing to do.
Of course, it means that it's harder to upgrade the detectors, for example.
It is, but you know, it's a kind of a one-time thing that happens. Like when we upgraded the high-res detectors, it was $1 million and it took 3 years. And you know, we were down for a couple of weeks while we installed it. But it wasn't too big of a ripple on the users. We were able to do it during a dark time run. But yeah, upgrades become much harder.
You showed a reflectivity curve for the secondary and tertiary mirrors for the APF, which had very good performance over a quite broad range of spectrum. And what's been used up to date for iodine cells is a much smaller range of spectrum.
Mm-hmm.
And I'm wondering what your plans short-term and long-term may be to use a larger amount of the spectrum.
Well, we'd love to use a larger amount of spectrum. We're only using about 1,200 angstroms right now. And that is, it's a fundamental limitation. It's all about gathering information. So it goes roughly as the square root of the number of lines. And we're at about 490 nanometers to about 610 nanometers. For G stars, K stars, M stars, as you probably know, the line density rapidly increases towards the blue. So if we could get down in the sort of 390 to 490 range as well, we'd pick up a huge number of lines and get, you know, at least factors of 2 probably gain. And that would be good. The Swiss are able to do that with their technique. So I've been thinking about making a different type of cell, and I've looked really hard at various types of cells. Iodine won't get you down there. Chlorine and bromine do almost the same as iodine, but they only push it 100 angstroms either way, basically. But there is a species that you can use to do this, and I have some money to put together a cell, but I just haven't had the manpower or the time to do it yet. And that is the species tellurium. Tellurium, it looks almost like iodine, but it works from about 360 nanometers right up to about 500 nanometers. So it's a perfect match to use in series with iodine. That's the good news. The bad news is that it has to be run at 500 centigrade. So, you know, it's right in front of your spectrograph slit, and it's a black body. Fortunately, it's not really a good black body. It's glass, right? So in the optical, it doesn't glow like a stainless steel puck would glow at that temperature. It's glass, right? And the calculations show it's probably going to be fine, but you got to put it in the Dewar and hide all the heating elements from any solid angle that could make it into the spectrometer. So there's some engineering involved, but I think we can probably deal with that. And if we could do that, we would essentially get all the goodies from the spectrum at that point. So maybe that'll happen someday.
If the laser comb ever is developed as a technology, would you have room to put something like that in place of a cell? Or? You
could. It wouldn't be necessarily in place of the cell. The thing about a laser comb, what he's talking about is having essentially a comb function. It's a pulse laser. It's pulsed at very high repetition rate and locked to a standard, and it creates a set of emission lines, a very fine grid of emission lines through the spectrum that you can use as a wavelength calibration source. The difficulty with that, of course, is how do you mix it into the beam? With the iodine cell, the cell is actually part of an interferometer that reaches out to the star, right? It's an experiment that's actually resonating with the star. Those iodine lines are interacting with the star's photons. So you've got this instrument that reaches all the way out to the star. With a light source that you are using to calibrate your source, it doesn't know about the stellar photons at all, and it doesn't care about them. So getting that light to go through your spectrometer in exactly the same way that the star goes through is an issue that no one has really completely grappled with. And the idea is, well, you use a fiber, and the fiber is like a funnel. You pour sand down a funnel, it comes out the other end. Who cares how you poured it in? It all comes out the other end. Well, real fibers aren't quite like that at these sorts of levels when you're talking about, 80 atoms of things moving around. So mixing it through a fiber may not be good enough. We don't know. These are all technical problems that are going to have to be faced by the people that do this work. My own sense is that since we're already below a meter a second, I don't think it's really going to buy us much, because your errors are the quadrature sum of a bunch of different things. Photon statistics is one of the big ones. I mean, this might help you on really bright stars. Most stars are too faint to get to those precisions anyway. Number two is the stellar jitter, which is often at least a meter a second or two, and so you're beating your head against that. So if you can do 1 centimeter a second, it doesn't matter, because the star's jitter is dominating it. And then the other things are like systematic errors that might help you with. So at least I'm not pursuing the laser comb myself, because I don't think it's going to really make much of a difference on what we do.
Your eta fraction that you mentioned, it's kind of blowing me away in its generosity. I didn't know that the state of the art in data right now was pushing it to that high a level. And the reason it's blowing me away is because, as you say, when you scale it up to galactic levels, the number of habitable planets is getting astronomical. How then do we account for the old Fermi paradox?
Boy, I tell you, there's probably a lot of people in this room that can answer that question better than I. Yeah, it's probably the best answer of all. We don't know. Whether they're out there or not, or whether they're trying to communicate or not, whether we just missed them in time, it comes down to the lifetime of a civilization, and whether it decides it wants to spread out among across the stars, whether it wants to try to communicate with us, and whether it's doing it in a way that we could even imagine. There's an awful lot of unknowns, but there certainly are a lot of places out there where such things could happen. That we know now. Yes. No, wait for the mic, I guess.
Yes, let's see, a couple of questions germane to the last point. What's the current status of theories about the formation of our moon? Is giant impactor uncontested at this point?
I'm not an expert on that. To my knowledge, that's the giant impactor sister sort of thing is I think the front runner out there now, based on geological stuff. It was a big hit on the Earth once long ago. I
mean that seems to have been one rare, a potentially quite rare phenomenon that that the Fermi enthusiasts cite.
That the fact that we have a moon makes us unique.
A large moon whose stabilizing the obliquity of Earth,
right.
The tides, filling clear water oceans with minerals. I just found out, in fact, there was a wonderful show that was on Discovery a couple of days ago that drew to my attention the fact that the orbital period, I think the rotation of Earth early on was 5 days rather than 24, and that the moon, after it was first formed, was 15,000 miles away rather than whatever it is now, 240 or...
Yeah, it's moving out slowly with time. Well, certainly it's a very complex problem, and the moon undoubtedly figures into the ability of the Earth to sustain life as it has developed. It's certainly part of the equation in ways that I don't think we fully understand. I mean, similar to plate tectonics and the carbon silicate cycle, all these things just, it brings biology and geology and all those things together in ways that are probably much more complex than we really understand at this point.
And let me ask a second question. There was one tantalizing remark that you made in one of your slides that showed it was during an occulting period of a planet where, I don't know whether it was APF, something being able to see an atmosphere around that occulting planet. Is that work that you folks do?
I worked on that system with one of my former students who's now teaching up here in the Valley. It was part of her master's thesis. There have been a few groups that have done. There's a group at Texas that has done it on several of the transiting planets. Dave Charbonneau and Tim Brown were the first to actually do it on this planet from space on 209458 using STIS, I believe it was, in the sodium line. So there's a handful of groups that are trying to do this. It takes a lot of signal to noise. So you either need a space-based platform that can stare for a long time, or you need a pretty big telescope and a high dispersion spectrometer to do this. And there's only a handful of those in the world, so it's some group using one of those.
In terms of prognosis and instrumentation funding, do you think we'll have instruments in the next 5 or 10 years that will be able to see spectra of atmospheres of planets? That would be the real...
It's tough. It'll probably have to be space-based. So, you know, 5 or 10 years takes at least that long to get something up there. There's a lot of things on the drawing board. I think it'll come. I don't know if it'll be in 5 and 10. It might be in under 20. That's why we're focusing so much on the nearest stars, because now that we know that the incidence of planets is very high, 30 to 50%, it makes sense now to look at the nearest stars, because you'll find planets. You'll find lots of them. And those are the ones that are going to be the easiest to characterize in those sorts of ways, whether it be a TPF mission or some other kind of thing. Yeah, I think that'll be the next step, the next logical step. It'll probably be a space-based mission.
One last question.
Are any of the stars that you're going to be looking at going to overlap the stars that the Kepler mission is looking at? And
we're not looking specifically in the Kepler field.
Okay.
Again, we're looking at stars that are typically closer than 100 light years. And the Kepler field, I forget how far away it is, but it's many, many times farther out than that. Their typical stars are, I guess, 12, maybe to 14th magnitude, something like that. Our faintest ones are about 14, I think. We typically like to work brighter than 10 if we can. And I think as time goes by, since Kepler will do so well on those kind of stars, it'll push us to even brighter levels. We're trying to find bright transiting planets, things that are 6th magnitude, 5th magnitude, to really be able to get in there and do work on not only their transiting planet, but on whatever else is floating around in the system. So that's going to kind of be the direction that we're going in, really nearby stuff.
Steve, as a token of our appreciation for you coming along, we have a type-in, SETI Institute type-in.
Oh, thank you.
And if you'll join me in thanking Steve for his great talk.
Thank you.